Hello and welcome back. Today we are talking about Chebyshev's theorem. Oops, there we go. Chebyshev's theorem. If you had not already watched my videos on, I would recommend normal distribution and the empirical rule. I would check those out first. But yeah, let's dive in. So Chebyshev's theorem applies to any data distributions regardless of its shape. As we should remember from the empirical rule can only be applied to a normal distribution that has a bell curve. Chebyshev's theorem applies to any looking distribution, including the bell curve, but typically we wouldn't use it for that. Chebyshev's theorem provides the minimum proportion of observations that must lie within k standard deviations of the mean, provided that k is greater than 1. Okay, so we have you should remember from a previous video, we would call this a bimodal distribution because it's got the two peaks here. We could not use the empirical rule for something like this, so we would use Chebyshev's theorem to estimate the number of observations within k standard deviations. And I'm going to repeat myself here, but just reminder, it will not work within plus or minus 1. That's what the k represents, the number of standard deviations. It must be used we are allowed to use decimals for k, so you could say 1.1, but more realistically, we'd use it for whole numbers like 2. Okay. Here's the formula. Formula reads P is our number of proportions is greater than or equal to, percentage of data. P is greater than or equal to 1 over k squared, with k greater than 1. And I misspoke before, P is the percentage of data, and k is our number of standard deviations. And a little note here, multiply results by 100 to convert to a percentage. So back to the first note here, actually, our answer should be in a percentage, so it's good to just always multiply by 100. We're going to get decimals out of this. K must always be greater than 1. K can be a decimal number, i.e. 1.5, 2.76, whatever. And this works for all types of distribution, symmetric, skewed, bimodal, or any unusual look and shape. Why does this matter? Unlike the empirical rule, which only works to approximate normal distributions, Chebyshev's theorem works for every distribution. There is a trade-off, though. It gives the minimum guaranteed percentage rather than an approximate percentage, and it does not work at 1 or less standard deviations. So the minimum, so we'll see what that looks like more, but it gives a minimum guaranteed percentage, not an approximate percentage. Okay. Some quick common values. Typically, we'll see k equal to 2, 3, or 4. And we work out the math. I'm not going to read it all, but when we work out the math, typically when we work within 2 standard deviations, we have at least 75% of the data. When we work with 3 standard deviations, it gives us at least 88.9% of the data. And when we work within 4 standard deviations, that gives us at least 93.75% of the data. Okay. Now, sometimes you're not always given k, and we have to find it on our own. So here's a little formula for finding k. We're going to see this formula a lot with z-scores. It's a pretty similar idea. And we're going to see a similar formula to this. There's one minor tweak to it. But anyway, this is our formula for finding k if we need to. K equals the absolute value of x minus mu over sigma, where k is our number of standard deviations, x is the observation or given value, mu is our mean, sigma is our standard deviation. And I just made a note here, not so much the x minus mu part, but these lines, if you're not familiar with them, when we put lines around values, that's our absolute value, which just means take the positive of it. Sometimes we'll get a negative. We need to only work with the positive. Okay. And I want to make it crystal clear the difference between k and sigma. K is the number of standard deviations we have, whereas sigma is just simply our standard deviation. Okay. And just quickly using our previous graph of the bimodal distribution, it will look something like this. Again, we can't work at plus or minus 1. So plus or minus 2 standard deviations is at least 75% of the data. And that's why I use the greater than or equal to symbol. The percent of data here will be 75% or more. That's what I mean by at least. Plus or minus 3 standard deviations is at least 88.9% of the data. and plus or minus 4 standard deviations is at least 93.75% of the data. Okay. All right. Let's look at an example. A data set has a mean of 80 and a standard deviation of 5. What minimum percent of observations lie between the scores of 70 and 90? All right. So as always, I list our givens. Our mean mu is 80. Our standard deviation is 5. And we're given two x values. So I label them x sub 1 is 70 and x sub 2 is 90. Okay. All right. Step 1, determine k. So I have a lot going on here. I'll break it down for you. Pretty much I give you two different ways we can determine k. We could determine it algebraically, and we could also determine it geometrically. Algebraically is the safest way, but once you get comfortable with this, you can actually do it pretty quickly geometrically. You can almost just do it in your head. But if we're not comfortable, I highly recommend practicing the algebraic way. You will get it right every time. Anywho, so algebraically, we use our formula. So now I did it twice here just to show we would get the same answer. It doesn't matter which x value we use as long as we take the absolute value. So the first way, I use x sub 2, and I use that because x sub 2 is the larger value and it's greater than our mean. So we take the absolute value of x sub 2 minus mu over our standard deviation. That's 90 minus 80 over 5, gives us 10 over 5, k equals 2. Okay, the second way I do it algebraically, I use our smaller value of 70, our smaller x sub 1, or our smaller x value, which is x sub 1. And I do this again just to show what happens when we get a negative. X sub 1 minus mu, the absolute value of that over standard deviation is absolute value of 70 minus 80 over 5 is negative 10 over 5. The absolute value of negative 10 is a positive 10, 10 over 5, 2. We get the same answers both times. Okay, so with these two different ways we found k so far. And then we can look at geometrically over here. Let's make sure. Okay, cool, we're all on the screen. So if we mapped out what this would look like, we would put 80 at our for our mean mu, and our standard deviation is 5, so we go up 5, up 5. Hey, 2 standard deviations gives us 90. Down 5, down 5. Hey, negative 2 standard deviations is 70. Okay, so we could see that 90 and 70 are both 2 units away from the mean in either direction. We don't concern ourselves with a negative going this way. We just know it's 2 to the left, 2 to the right. So because it is 2 standard deviations away from the mean, looking at it like this, we can quickly confer k equals 2. Okay, 2 different ways to do it. All right, anywho, after we find our k, step 2, apply the formula. So p is greater than or equal to 1 minus 1 over k squared equals 1 minus 1 over 2 squared, because k equals 2, equals 1 minus 1 over 4, because 2 squared is 4. This next step here, I'm just going to highlight it so it pops out. I rewrote 1 as 4 over 4 to make our subtraction easier when we have a common denominator. When we have a common denominator, when we subtract fractions, we just subtract the numerator. 4 minus 1 equals 3 over 4. And we get our answer of 0.75. Multiply it by 100, 75%. So at least 75% of observations must fall between 70 and 90. Easy peasy. And we should recognize that's one of the common values we're given over here. When k equals 2, it's always 75%. Excuse me. That's something you will see very often. Okay. Easy peasy. All right. Some common mistakes. Using Chebyshev's theorem when asked specifically to use the empirical rule. If you have a normal distribution, you should just always use the empirical rule. Your teacher may ask you to use Chebyshev's on a normal distribution, and that's fine, but just make sure you're doing what you're asked. Forgetting that k must be greater than 1. If you get a value 1 or smaller, you can't use Chebyshev's. Don't do it. Another common mistake, forgetting to square k in our steps here. Right here in our denominator, k is always squared. Cannot forget that. And thinking the result is an exact percentage instead of a minimum guaranteed percentage. Again, this tells us the Chebyshev's theorem tells us the minimum percentage within k deviations. Okay, so for 2 at 75%, it means that 75% or more of observations fall between that. That's what at least means. Okay, the least it could be is that percentage. Comparing to the empirical rule, Empirical rule only for approximating normal distributions, and it gives the percentages of 68, 95, and 99.7, which we should know from the previous video. And then Chebyshev's, it works for any distribution, and it gives the minimum guarantee, which I just went over. And I'm also just going to include here, only applies to more than one standard deviation. I think that's a fair thing to include that we have to keep in mind. Okay. All right. And here we have a practice problem. A data set has a mean of 50 and a standard deviation of 8. What minimum percent of observations must lie between 26 and 74? Feel free to pause here and take a stab at this problem. All right. Hopefully we paused and looked at it. Let's take a look at the solutions. So, as always, I list my givens. We are given that the mean is 50, the standard deviation is 8, the smaller test score, x1 is 26, and the larger, are they test scores? Whatever, just observations. The smaller observation is 26, the larger observation is 74, x of 1, 26, x of 2, 74. All right, so we find our k. I just picked the larger one just to avoid dealing with the negative. You could have picked x of 1. It doesn't matter. You get the same answer. X sub 2 minus mu over standard deviation equals 74 minus 50 over 8 equals 24 over 8. K equals 3. Okay. Once we find our k equals 3, we plug it into Chebyshev's. P is greater than or equal to 1 minus 1 over k squared, which equals to 1 minus 1 over 3 squared, which equals to 1 minus 1 over 9. Turn the 1 into a fraction. 9 over 9 equals 1. We have our common denominator. 9 over 9 minus 1 over 9 equals 8 over 9, which is approximately 0.889. Multiply that by 100, 88.9%. So we could say that the minimum number of percentages, the minimum percent of observations that lie between 26 and 74 is 88.9%. Cool. And that's everything I have for you on Chebyshev. Thank you for tuning in. As always, a link to the notes will be included in the video description, and I will see y'all next time. Take care.